All right, so get excited. We're going to see how to figure out what method to use with line integrals, right? So we have the regular parameterization with line integrals in 16.2. Then we had the fundamental theorem of line integrals that we saw in 16.3, and then we saw Green's theorem in 16.4. So the question is, when do we use which method? Well, let's get started with this problem. Okay, this is number 2 in the review day packet. So here, I wanted to first determine whether f is conservative. So let's just determine that. If f is conservative, then I know that p equals f sub x and q equals f sub y. So then I see if their second mixed partial derivatives are equal to each other. So I find p sub y, which is 2y, and I find q sub x, which is 2x. Those are clearly not equal, therefore f is not conservative. So again, f is not conservative, so I can immediately rule out fundamental theorem of line integrals, because I know that I can only use fundamental theorem of line integrals when f is conservative. So here, if I already know if f is not conservative, I cannot use fundamental theorem of line integrals. Okay, so moving forward, part B, now I want to evaluate the line integral. Here I have a line segment from 4, 0 to 0, 3. If I just have a line segment by itself, right, I don't have a closed curve. And because I don't have a closed curve, I cannot apply Green's theorem either, because Green's theorem, one of the 4 requirements is that the curve must be closed. So I can't use Green's theorem because this curve is not closed. I can't use fundamental theorem of line integrals because f is not conservative. So the only thing that I could do is just perform this line integral normally by using parameterization. So I'm going to parameterize here. I have a line segment. I have my starting x value is 4, plus the difference in x values. I go from 4 to 0, so I have to subtract 4 in my x, minus 4t. And my y starts at 0, and I go up 3, so 0 plus 3t. As usual, line segment always ranges between 0 and 1. So then I find my r of t. My r of t is just x comma y, and then I take the derivative r prime of t, which I get the following. Now I could plug into my line integral. So f of r of t, I take my x and y from my r of t and plug it into f. So I have y squared, my y is 3t, so I plug that in, 3t all squared. Then I have x squared, and x is 4 minus 4t, so I have 4 minus 4t all squared. I dot that with r prime of t, so I dot it with negative 4 comma 3. I also know that for line segment t is between 0 and 1, so I could plug that in. And now I just have to simplify using dot product, and then I can integrate. Right, so I compute the dot product, and now I can integrate. You can do the rest on your own, right? The point of these problems is just to kind of figure out what method to use, so I'm not going to actually integrate this. You all know how to integrate this. So we'll skip the integration, and we'll move on to the next problem. Again, the point of these is to determine how exactly do I start the problem. Let's look at number 3, or the second example. So here I again want to determine whether f is conservative. So I have p sub y is e to the x cosine y, f q sub x is e to the x cosine y. So they're equal. So my partials are equal. They're also continuous in R2, because I could see here that the domain is R2. There's nothing that I could plug into x and y to make this undefined, so the domain is R2. So I have equal and continuous on R2, and now I just have to check that R2 is open and simply connected. Right, so verifying that R2 is open and simply connected, R2 is open because it does not contain any boundary points. If I think about R2, it just extends on forever. Right, R2 extends on forever in every direction, so it doesn't contain any boundary points. And it's simply connected because any simple closed curve that I draw in R2 will only contain points in R2, right? So any point inside that simple closed curve will only contain points in R2. So that's why R2 is open and simply connected. Okay, you should explain that. I'm not going to write it out because I've done it enough in class, but you should explain why R2 is open and simply connected. So now we have all 4 conditions, so that tells us that f is conservative. So let's think about this for a second. In part B, I want to evaluate the line integral over some curve from 0, 0 to 2 comma pi. And if I look at this, this is not a closed curve, so again, we cannot use Green's theorem. So that already rules out section 16.4. If I think about section 16.3, I could use fundamental theorem of line integrals when f is conservative. So maybe I could use that. If I go back to 16.2, maybe I could parameterize this as well and then go ahead and plug in. We don't want to parameterize when either the parameterization looks like it's going to be complicated or the integration looks like it's going to be complicated. So if I try my parameterization, I get x equals t and y equals pi t squared over 4. Then if I try to plug that parameterization into the vector field, I get this, okay? And when I set up my line integral, I have to dot this vector with r prime of t. So you could see here that it's going to get very complicated because I'm dotting this vector with another vector, and then I have to integrate that, and this already looks complicated enough to integrate. So if you're dotting it with something else, it looks like it's going to get even worse. So that kind of tells me, okay, maybe I don't want to use section 16.2. Maybe I don't want to parameterize. Okay, another key thing for not wanting to parameterize is the path that we're given. While it's doable, right, it's just pi over 4 times x squared. We have y equals pi over 4 times x squared. That doesn't seem too bad. But we want to parameterize when we have something simple, like y equals x squared, or y equals square root x, or something even simpler than y equals pi x squared over 4, right? And again, also, if you try the parameterization, you plug it in, we could see it's just going to get really complicated. We didn't even dot it with r prime of t yet, and it already looks complicated to integrate. So that tells us, let's stitch 16.2. We know that f is conservative, so let's go ahead and apply fundamental theorem of line integrals. First, we'll need to find the potential function, f. So to find the potential function, we could either integrate this with respect to x or this with respect to y, because since f is conservative, this equals f sub x and this equals f sub y. So it looks like it's easier to integrate this with respect to x, so let's go ahead and do that. Once we integrate with respect to x, remember, y is considered constant here, so my constant of integration is in terms of y. Then I go ahead and take the derivative. I already used p with respect to x, so now I have to take the derivative with respect to y. So I take the derivative of this function with respect to y, and then I set it equal to f sub y, which is the same thing as setting equal to q. Now if these two are equal, I solve for g prime of y, which is y. So if g prime of y is y, I now need to find g of y. The reason why I want to find g of y is because that f equals this, and so I need to plug something in for g of y. So I just integrate to get g of y. And again, g prime of y is y, so I plug that in, and I get y squared over 2 plus k. You can use plus c if you want, but typically we'll use plus k here. And now I just have to plug that into here. So I found my potential function. Again, what this means is that when I find the gradient vector of this function, I get this. I get this vector field, right? And that's what it means to be conservative, is I can find some scalar function out there, namely this function, such that when I find the gradient, I get exactly that. So now, by fundamental theorem of line integrals, I could take that potential function, right, and I just evaluate it from 0, 0 to 2, pi, because that's what the path is between, right? Who cares what the path is? It doesn't even matter what the path is, because as long as f is conservative, we know that the line integral is independent of path. So we don't care about what the path was, right? All I care about are the endpoints, because no matter what path we choose, it's going to give us the same result. So I plug the endpoints into the potential function. Again, we can apply the fundamental theorem of line integrals whenever f is conservative. I could just set the constant of integration equal to 0, because it's just going to cancel out anyway when I plug in my bounds. So I plug in my bounds, 2, pi, and then 0, 0, right? X equals 2, y equals pi. I plug it in. Sine pi and sine 0 are both 0, so I'm just left with pi squared over 2. Much easier than parameterizing and figuring out some integral that looks like it's going to be very complicated. So looking at the next one, again, determine if f is conservative. So we could see here that both p sub y and q sub x equal the same. They're both equal to 12x cubed y. So these partial derivatives are equal, and they're also continuous on domain R2, because it looks like the domain is R2, right? There's nothing I could plug into x and y that would make it undefined. Right, so we have equal and continuous on R2. Make sure you specify what's continuous. Is it the original vector field, or is it the partial derivatives here, right? So if you just write it in the same sentence, then it's clear that we mean that these partials are continuous on R2, which is what I'm looking for. Again, look at the domain and make sure that the domain is open and simply connected. I would expect you to explain why it's open and simply connected on the final. So you would go ahead and explain that, same as I've explained a million times in class. And then from there, as long as all four conditions are satisfied, we know that f is conservative. So now that I know that f is conservative, I know that I could apply fundamental theorem of line integrals. So again, I don't want to apply Green's theorem because I can't graph the function. And if I can't graph the path that I'm on, how am I going to set up my bounds for the region for the double integral? So I can't use Green's theorem. I can't use the parameterization, right? Both of those are going to get really complicated. So instead, I could think about applying fundamental theorem of line integrals, but there's an even easier method. Because with fundamental theorem of line integrals, it's still going to take a lot of work. If I look at my path is actually closed. I don't know how to graph it, but I know that it's going from 0, 0 to 1, 1, and then back to 0, 0. So I know that my path is closed. Therefore, I could just say that the line integral is 0 by this theorem that we saw in section 16.4. So I don't exactly know how to graph my path here, but I know that it goes from 0, 0 to 1, 1, and then back to 0, 0. So therefore, I know that the path is closed, and again, if the path is closed and f is conservative, then we learned in section 16.4 that the line integral is just 0. So know that fact so you can save yourself some time. Instead of going ahead and finding the potential function and then applying fundamental theorem of line integrals, we could save ourselves a ton of time if we just recognize that the path is closed and that f is conservative. So again, you could just say the line integral is 0, but I'm looking for two conditions to just check, right? You have to make sure you state that we could say it's 0 because f is conservative and that c is closed. In the previous example, we had to apply fundamental theorem of line integrals because it went from one point to another, so the path was not closed. So we couldn't just say that the line integral was 0 because, again, the path is not closed, whereas here it is. So again, if you get f is conservative, make sure you check whether that path is closed, because if the path is closed, we could just immediately say the line integral is 0. If the path is not closed, then we go ahead and apply the fundamental theorem of line integrals. Moving on to the next example, part A says check whether f is conservative. I found the parcels and we could see that they're not equal, so f is not conservative. So if f is not conservative, we immediately know two things. First of all, we cannot apply the fundamental theorem of line integrals. The second thing that we know is that the line integral is not 0 because we can only assume that it's 0 when f is conservative and the path is closed. That leaves us with two options. We could either do parametrization or we could do Green's theorem. So while we could do parametrization here, right, we have two different paths, which means we have to do two different parameterizations. So let's just see if we could use Green's theorem, because if we can, it'll save us a ton of time. So I graph my path here. I go from 0, 0 to 1, 1, and then back to 0, 0. So I can see here that my path is counterclockwise. It's closed. It's simple because it doesn't cross itself, and it's piecewise smooth. So it satisfies all four conditions of Green's theorem, so we could go ahead and apply Green's theorem. So we go ahead and use Green's theorem because all four conditions are satisfied here. Oh, I forgot to use green marker. Let me start over. Much better. So we have q sub x minus p sub y, which is 9 minus 6. And now we look at our y bounds. Y is bounded below by y equals x and bounded above by y equals square root x. And x is between 0 and 1. Now we can go ahead and integrate that. So again, you can finish the rest of the problem on your own. Nothing super complicated here. You just perform reverse power rule. I trust that you could do it on your own. Again, the main thing to take away here is that if my curve satisfies all four conditions, regardless of whether f is conservative or not, that has no effect here. It doesn't matter whether f is conservative. All that we have to know is that the curve is closed, simple, counterclockwise, and piecewise smooth, and if that happens, then we can go ahead and perform Green's theorem. The last example, notice the similarity between this one and the previous. It's basically the same thing. You're literally doing the same exact thing, but let's see how it's different. Here, all you're told is that we have some region bounded by y equals square root x and x. There's no mention of counterclockwise going on, right? There's no mention of how we're traveling through this path, so we can't determine whether it's counterclockwise or not. However, like I said in class, if we see a circle around the integral, that immediately indicates positive orientation, which we know is counterclockwise. So here, this immediately tells us that we have counterclockwise, so that condition is satisfied. We can also see that the curve is closed and simple, right? And it's also piecewise smooth. So just like the previous example, we go ahead and use Green's theorem because we have that all 4 conditions of the curve are satisfied. The only one that we're missing from the description of the problem is counterclockwise. But again, if you see that circle there, that tells us we immediately know it's a positively oriented curve, meaning it's going counterclockwise. And notice here, the notation is different. This is the line integral with respect to coordinate variables, part 2 in section 16.2. In the previous example, we had part 3 of section 16.2, which is a line integral over vector fields. But again, as I mentioned in section 16.2, it's the same thing, just approaching it in a different way. So this is going to get you to the same exact answer. We still go ahead and apply Green's theorem, because again, it's just writing it in a different way. We're doing the same thing. So you would go ahead and apply Green's theorem the same way. Right, so first we would need to verify C is closed, simple, counterclockwise, and piecewise smooth. Once we write all that out, we just convert it to the double integral and do it the same. This is Q, this is P. Just like we would if we were given a vector field, right? And then we calculate the partial derivatives and go from there. So again, this is P, this is Q, very similar to a vector field here. We just take the partial derivatives and plug in. We're going to get the same thing as the previous example. We set up our bounds just like we did in the previous example. Nothing changes here, and then keep going.
Let's take a look at a little flowchart to help us understand when to use which method. On the left side over here, we have a line integral with respect to arc length when we have ds as our differential. And the only way that we could integrate this with respect to arc length is the parameterization that we saw in 16.2. There's no other method for that. All of the other methods that we learned correspond to line integrals with respect to coordinate variables and or over vector fields, parts 2 and 3 of section 16.2.
If you're given coordinate variables or vector fields, there's really only 4 options here, okay? The line integral is 0 if f is conservative and the path is closed. Applying fundamental theorem of line integrals if f is conservative but the path is not closed. The curve is closed, simple, counterclockwise, and piecewise smooth. We go ahead and apply Green's theorem. And lastly, we parameterize. The parameterization could be in 2 different ways, depending on whether we're given a line integral with respect to coordinate variables or a line integral over vector fields. And you could see the difference in section 16.2. So again, if you check all of this and you can't figure out what to do, so you have to go back to here and do a parameterization, but it's just obnoxiously complicated to parameterize, then go back and check to see if you can do any of these, because the most difficult parameterization you have here is going to be like y equals x squared or y equals square root x, or a line segment or a line or a circle, right? You're not going to get something that complicated. So if it looks really complicated, go back and check if you can do any of these.